Okay, we have made it to chapter 9. It is time to meet another conservation law. And building up to that law for the conservation of linear momentum, we're going to develop some of the infrastructure for what momentum is, how to express Newton's laws of motion in terms of momentum, and the idea of the center of mass of a system of objects. Two of my favorite images for highlighting the ideas of momentum and collisions and center of mass are here on the cover page for the chapter. It's just sitting and playing pool is a great way to experiment with the ideas of collisions and conservation of momentum. And actually, with putting spin on the ball, so the spin has a quote unquote English to it, you can start to do some things that will at first seem counterintuitive until you process the idea of angular momentum as well. But that comes from another chapter. We'll get there, not just quite yet. So a great way to practice out these ideas of conservation of linear momentum is just play a game of pool. Another thing illustrated is the role of the center of mass. So there's a dot painted onto this wrench. And you'll notice this is a sort of image where the shutter is just opened for a brief instant, and then you're getting the location of the wrench at discrete instants of time, but in the same exposure. You can accomplish the same thing with a stroboscope instead of controlling it with a shutter. What I want you to notice is that every interval of time, which the time interval is equal for all of these exposures, that white dot is advancing the same distance. And as that is happening, the wrench is rotating about that white dot. Okay. So one of the rules of the idea of the center of mass is that effectively all of the mass of this wrench will act as if it's concentrated at that one point, which is conveniently highlighted with the white dot painted on, right? And so the trajectory of the wrench is equivalent to the trajectory of the center of mass of the wrench. So we could take this extended rigid body, the wrench, and treat it as just one mathematical point and get its entire trajectory. And then what is the wrench doing in the meantime? Well, if it is truly a rigid body, and we'll learn later how to relax that, but if the wrench is truly a rigid body, then the only thing that it can do is rotate about its center of mass. So the motion of a rigid body is going to be fairly simple, at least for this distribution of mass. It will have uniform translation of the center of mass, and then the rigid body will rotate about the center of mass. You can play a little trick with this, and you might be aware of this already, but there are objects like a tennis racket is probably the most famous example. If you try to spin a tennis racket, there are two rotation axes that it's stable to rotate around. So it can, well, anyway, play around with it and you can find out. The long axis or the shortest axis, it is a stable rotation. But if you try to rotate a tennis racket about the intermediate axis, it's actually unstable and it'll start to tumble. So that's why I'm trying to be a little careful with this wording about, for a rigid body, the most complicated thing it can do is to rotate and translate. Center of mass translates uniformly, and then, or is accelerated, and then the object will rotate about the center of mass. But you could have a mass distribution that is unstable. So if there's some small perturbation, it'll go into a tumbling motion. But that's a little bit beyond the math for this class because you need essentially rotation matrices to describe things. Anyway, so fun things to play around with. I would encourage you to play a game of pool uh, with someone from class or uh, with someone else, and see if you can use your knowledge of what we're going to learn are elastic collisions to your advantage. Um, and then also um, to play around with rotations, which we'll get to a little bit later in the class. But as a prequel to that, try to spin a tennis racket about its three different axes of rotation and see what happens. All right, center of mass. So the first step in this chapter is we're to try to define clearly what center of mass is. So if I have some system of particles, each of those particles has its own center of mass, then the center of mass of that system of particles is going to be a point in space. There need not actually be any mass there, but is a point of space that represents the object in the following way. That point will act as if all of the system's mass was concentrated there, and then external forces will act as if they're applied at the center of mass. You might have heard the term the center of gravity. If the system of particles is in a uniform gravitational field, then center of mass and center of gravity are identical. They'll be at the same location. If the gravitational field is varying, then center of mass and center of gravity could be different things. To just keep that in the back of your mind as a possible complication that can arise. But we're talking about things like near the surface of the Earth. Gravitational field is pretty uniform for any sort of system. So if the system that you're going to deal with is made out of discrete pieces, like I have some stack of blocks, or I have a stack of coins, or whatever it happens to be, those discrete objects, each one has their own center of mass, and I can find the center mass of the collection with the following sums. So one is a scalar. I get the total mass of the system by just adding up the mass of all the pieces. Fairly straightforward. And then the vector describing the center mass position of the system comes from 1 over the total mass of the system times the sum where the center of mass of each part, the r sub I vector, is weighted by its own individual mass. So the larger the mass of a component of a system, the more contribution it makes to the center mass of the system, which is reasonable. Okay, so if I have discrete objects, I can find their center of mass by getting the total mass and then doing the sum over the center mass of each individual piece. And we'll try that in just a little bit. Obviously, some objects are not made out of like discrete blocks, Lego blocks, or coins, or whatever it happens to be. It's a continuous distribution, like for the Earth as a whole, or center of mass of the fluid in my coffee cup, for example. Those are continuous mass distributions specified by a mass density rho. And just for sake of being able to write something down, I write this out in terms of Cartesian coordinates. But obviously you can make a coordinate transformation to spherical coordinates or cylindrical coordinates or confocal ellipsoidal coordinates or whatever your favorite coordinate system happens to be. But we live in a three-dimensional world, so getting the total mass now means integrating the mass distribution over all three of its coordinates. So if you're not familiar with the idea of having like a triple integral, the basic idea is you just pick one of these coordinates that this row is a function of, and you would integrate over, say, x first, and then what's left you would integrate over y, and then you're down to an integral that just depends upon one coordinate. But this can get sort of tricky because your boundary terms, the upper and lower bound for each of the integrals could depend on the coordinates themselves. So you have to keep that in mind. All right, that is how we would define the total mass of a continuous mass distribution, given some function for the mass density rho. And then I could get the Cartesian center of mass coordinates by integrating over 1 over the total mass, and then this triple integral over the position vector times the mass density times the volume element. In general, it is going to be, quicker and more expedient to look up the center of mass for various distributions of mass, like a sphere or a hollow ball or a ring or a disc or a rectangular plane, so forth. So a lot of these standard integrals are just basically done once, and you can look up what the answer is. If I have a uniform object, we have some intuition about this. The center of mass is going to have to lie at the point of symmetry for the object. So if I have a ball and the ball is uniform mass density, then the center of mass has to be the geometric center. If I have like a square as a two-dimensional object and it's uniform mass density again, then the center of mass is going to have to lie at the geometric center. If I have an irregular object, experimentally, you just let it hang down. Because then it is going to settle where the center of mass of the object is at the lowest point it can be. And that tells you that the center of mass has to lie along the direction straight down for that object hanging. And then you can just hang it from another point on it, and the center of mass will have to be at the intersection of those lines. So they're the basic physics of a plumb bob. Okay, so let's try an example and have you guys work this out. So I've got a coordinate system. Ugh, boy, that was bad. So there's X, and there is Y, and we have rods that are of length L and mass M aligned along the coordinate axis. One is along Y, one is along X. They are both of mass M and length L. So for that system, those two rods, where does the center of mass lie? So think it through, might be able to get it intuitively, might want to apply the sums that we had before. And then also don't get too upset. I think the first time people answer this, they often get it wrong. So give it a thought, see which one of those answers makes sense, and then we'll talk about it together. All right. So it's going to be L over 4 along the x direction, L over 4 along the y direction. So we can eliminate two of these because they're not symmetric, and yet this object is symmetric. It extends just as far along the y as it does along x. And let's think about it for just a little bit. So the center of mass of the one along x lies at its geometric center. So that's an x coordinate of L over 2. And then the one along the y-axis, its center of mass lies at its geometric center, which is an x coordinate of 0 and a y coordinate of L over 2. And they're both contributing an equal mass. So if we just look at the equation for the x component of the center of mass, I have 1 over the total mass, which is 1 over 2m. I will have the x coordinate of the center of mass of the first rod, which is 0, and then the x coordinate of the center of mass of the second rod times its mass. So it's going to be m L over 2. And then, clearly the m's cancel out, and we'll have x coordinate of the center of mass. It's going to be L over 4. And the same argument along the y-axis gives you that its center of mass is at L over 4 as well. So, and that gives us center mass of the whole system. It's right about there. And again, just to emphasize, it's no problem that the center of mass of that system is not where any of the system itself is. Perfectly fine. Makes it hard to balance, but not an issue. Let's clear up a little bit. One of the utilities of finding the center of mass of a system is you can work in that as a reference frame. So once I have the center of mass of a system of particles, then external forces are going to act to accelerate the center of mass. And so we could split the motion into how does the center of mass of my coordinate, how does the center of mass frame of reference accelerate due to external forces? And then we could deal with internal forces, which give rise to conservation of momentum and motion in the center of mass frame. So this is one of the standard simplifications that emerges out of Newton's laws of motion, that I could do a coordinate transformation into the center of mass frame of my system. All the external forces, all that they do is they accelerate the origin of that center of mass frame. And then I have motion within the center of mass frame itself. So very useful idea, obviously for things like binary stars or multiple star systems like a globular cluster. Very useful idea. And then aesthetically, the motion of fireworks, say like the 4th of July or New Year's Day, the fireworks shells initially fired, and after some period of time set by the fuse, it's going to explode and give the shower of sparks. But that entire shower of sparks has to move in such a way that the center of mass of their system keeps following that same parabolic trajectory. So the shape that you see for like that rosette in the explosion of fireworks is all set by the fact that the explosion itself can't change the momentum of the system. It's an internal force to the system. And so I could go back at any point in time and add all those pieces back up together and just follow the center of mass of the exploded shell, and it will follow that same parabolic trajectory from kinematics from way, way, way at the start of the semester. So it's a nice way to think about how motion decomposes. External forces like gravity are going to accelerate the center of mass of the system, and then you'll have internal forces that cause the explosion itself. All right, and we'll have an example using this idea in just a second.